Hello students. This video lecture will cover section 12.4, angle measures and segment lengths in circles. Our learning goal for this lesson is to be able to find measures of angles formed by chords, secants, and tangents, and to be able to find the lengths of segments associated with circles. We've talked about tangents already. A tangent line is a line that touches a circle at exactly one point. We've talked about chords. Chords are segments whose endpoints are on the circle. And so we need the definition of a secant. A secant line is a line that intersects a circle at 2 points. So in this case, we have an example of a secant line, line AB. So let's take a look at our first theorem. These two theorems give us the formulas required in order to find the angle measures associated with lines that intersect circles. So here you can see that theorem 1213 gives us the formula in order to find the measure of an angle created by two lines that intersect inside the circle. So when two lines intersect inside the circle, we can see that we take the sum of the two intercepted arcs and divide that by 2. Theorem 1214 gives us the formula for how to find the angle measure associated with lines that intersect outside of a circle. So the different ways that lines can intersect with a circle. They could intersect inside the circle, which is what we saw in theorem 1213. We could have two secant lines that intersect outside the circle, in which case we're going to cut off two different arcs. We could have a secant line and a tangent line that intersect outside of the circle, in which case we'll get these two arcs, x and y. And then finally we have two tangent lines that intersect outside the circle. So one of the things that I like to tell students to try to remember is when they intersect inside the circle we add, and when they intersect outside the circle we subtract. So let's take a look at a few problems. In the case of problems like this, I like to try to identify what I'm actually trying to accomplish. So what I like to do is I like to mark the different problems. So here I'm marking the ones where the circle is intersected inside the circle with blue star, and I'm marking the circles where the lines are marked outside with a red star. So let's start with the blue stars first. Since this angle is inside the circle, we're going to add. Remember, intersections inside the circle we always add. So x is going to equal half of the sum of 46 plus 90. So this is going to give us half of 136. And so the measure of x in this case is going to give us 68. So this is a 68-degree angle. Now the second question has a slight wrinkle thrown into it. You can see they actually gave us the inside angle and one outside angle. So as we're solving for x in this case, we're actually going to have to put the 35 outside. We're going to have to set that equal to half of x plus 30. In order to get rid of the 1/2, I'm going to multiply both sides by 2. So I get 70 equals x plus 30. And if we subtract 30 from both sides, we get that x in this case is going to be 40. So in this case, this is a 40-degree angle. So this question on the top right is probably one of the easier questions on the entire page. Since we're dealing with an intersection that is now outside of the circle, and we're dealing with tangent lines here, in other words lines that touch the circle at only one point, we have two arcs that cut off the entire circle. So we can actually take 360 and subtract the 110 and find that W is in fact 250 degrees. Now we can confirm that with the formula. We have 70, the outside angle is going to be half of the difference between 250 and 110. So in this case, if you subtract here, you get 140, and half of 140 is in fact 70. So the formula does work. The nice thing about two tangent lines, though, is it gives us the entire circle. So if we're given one of them, we can figure out the other one by doing subtraction from 360. So the bottom left question, we're actually looking for the angle at the intersection. So we're going to say that y in this case is going to be equal to half of 110 minus 30. Again, remember, since the intersection is outside of the circle, we want to subtract the smaller one from the larger one. So 110 minus 30 is 80, so we have half of 80. And half of 80 gives us an angle measure of 40 degrees. And the final question, we're given the outside angle, so we're going to set that equal to half of the farther one minus the closer one. So we have half of 95 minus z. So to get rid of the 1/2, I'm going to multiply both sides by 2. I get 40 equals 95 minus some number. And so we find that z equals 55 degrees. The difference between 95 and 55 is in fact 40. Okay, so let's look at one of the possible real-world applications of this. We have a satellite which is in a geostationary orbit, meaning it follows the same spot around, and it's following around the equator. It has a viewing angle of Earth formed by the two tangents to the equator. The viewing angle is about 17.5 degrees, and it asks us what is the measure of the arc of Earth that is viewed from the satellite. So based on the formula we know that 17.5 is equal to a half of the two intercepted arcs were subtracted. So we have the measure of AEB subtract the measure of AB. Now this is oftentimes where people get stuck because they don't know what to do here. Well, if you think about it, the entire circle has to be 360 degrees. So if you know x, a lot of people want to try to put y. And that's fine, but then you have two variables in a single equation and that's unsolvable. So instead of writing it as x and y, I like to write it as x and 360 minus x. So in this case, we end up with 17.5 equals half of, and then by substitution, the measure of AEB equals x, and I'm going to subtract from that the measure of AB, which we've now established as 360 minus x. If we multiply both sides of this equation by 2 to get rid of the 1/2, we find that 35 equals x minus 360, and then negative x is going to give us plus x. So we're going to add 360 to both sides. So we have 395 equals, we have x plus x, so we have 2x over here. So when we divide both sides by 2, we get x equals 197.5. So this arc over here is 197.5. Now that's fantastic, but we're looking at what the satellite can actually see of Earth. So we want to take its complement from 360. So we actually want to know what 360 minus 197.5 is, and we find that this satellite can see an arc of Earth that is approximately 162.5 degrees. So this is the final answer to the question. The second part of this lesson involves finding the lengths of segments related to circles. So we have three formulas here which are really important, and these are the three potential cases with which lines could intersect circles. I would recommend writing these formulas down so that you have access to them on any potential tests or quizzes. So let's look at actually using those formulas. So first let's identify the different types. This intersection is outside the circle but does not involve any tangent lines. Same with this one. This problem involves an intersection that is within a circle. And this intersection involves an intersection outside the circle with a tangent line. So with the formulas written down, we can see that we want to multiply 6.5 times m, and that's going to equal 3 times 7, or 21. So I'm going to write this as 13m over 2 equals 21. So then 13m is going to equal 42, and therefore m is going to equal 42 over 13. And to the nearest tenth, this is about 3.2. The second type of problem I always remember as the sum of the two times the outside equals the sum of the two times the outside. So in this case, I would set this up as 6 plus 8 times the outside 6 equals 7 plus y times the outside 7. So 6 plus 8 is 14, and if we multiply that by 6, we get 84. And that's going to equal 49 plus 7 times y. And if we subtract 49 from both sides, we find that 35 equals 7y. And so y must equal 5. Here we have a very similar problem, just with larger numbers. We have 20 plus 14 times the outside 14 is going to equal 16 plus x times the outside 16. On the left-hand side, we get that this is 476, and that's going to equal 256, 16 times 16, plus 16 times x. So, subtraction, we get 220 equals 16 times x, and x here is going to equal about 13.75. And the final question up top involves a tangent line. So in these cases, we take the sum of the two, the same as we've done with secant lines. So we have 16 plus 8, and we multiply that by the outside, 8, and we set that equal to the tangent section, z, but the z gets squared. So 16 plus 8 is 24, and when we multiply that by 8, we get 192. So 192 equals z squared. And so taking the square root of both sides, we find that the square root of 192 is 8 times the square root of 3. So that concludes this video lecture, section 12.4, angle measures and segment lengths. Hopefully you took the time, as I recommended, to write down the formulas required. And if you have any questions, I'll see you soon.